Hello everyone. This is going to be our second last topic that we're doing in our circular and oscillatory motion section. This is topic 7. It's on superposition and interference. And one of the reasons why I'm going to make a YouTube video for this particular lesson is because it's actually quite short. This is actually a very simple little section. What I'd like to do is actually show you a little applet, a little Java applet that's going to help hopefully show and demonstrate the physics principle that I want to diagram. And once you understand the principle of superposition and how that works with interference, then it's really the idea. There's no math to this one. It's all about understanding. We do have one math equation we're going to do at the very end, but that's just to kind of wrap this all up and bring this all together. So our main concept today is to try to explain to you what interference is. And I've got a diagram that kind of illustrates interference, but rather than just show this diagram, I also have a little applet right here that you can see. So maybe here's the best way I can start is that rather than talk about these waves right here, one of the best ways of doing this in class, and I probably will still do this anyways, but is to use a spring, and you kind of send a pulse through a spring, right? So watch this little applet as I send a pulse through the spring, right? As I give it a little pulse. You can kind of see, I'm not even doing very well. I think this little thing right here works better. If I send a little pulse through it, you can see how it waves back and forth, right? Now, this is a little pulse. This is a bit of a wave that's going on here. We've learned about characteristics of waves from last day, so things like amplitude, period, where the crests and the troughs are. One of the reasons why this isn't working so well, though, is my dampening is on too high. Can you see how it's at 50? I'm going to drop this down a little ways. Actually, I'll drop it all the way down to 0, so that when I send a pulse through it, you can see that the pulse goes, and it's actually going to flip over and return. And because, in theory, there's no friction right now, you can see that there's a pulse that's been sent, right? Now what I'm going to do is I'm going to send another pulse, and you're going to see how it's kind of cool how they interact with each other. I can send a third pulse, right? And you get all sorts of really cool patterns out of this. Right? Every time I've added a new pulse, we get kind of a new pattern. Now, at some point, you can kind of see how some of these are getting kind of higher, right? Like at some places, it's still very, very flat across. But if I send enough of these pulses going on here, you're starting to see some constructive interference. And if I could maybe pause this for a bit. Constructive interference is this constructive word right here. It's where two pulses are going to meet up with each other. And they're going to add to each other. And they're going to overlap. And if you look at this diagram I've got right here, constructive interference means that they're going to get higher as they phase through each other. Let me try that again from the top with the simulator here. We'll restart it. I'm going to send a pulse through. And then what I'm going to try to do is I'm going to try to, the problem is that it's actually on a fixed end right there, so I'm going to send a loose end. And hopefully what we'll see is it just comes back right the way it came. Okay. So what I'm going to do now that it's on this loose end, see how it's going to stay upright and then turn around and go backwards? What I'm going to do is I'm going to do this. Ready? Now I'm going to send this one here. And look how they went together there, right? Watch again here. They're going to join together. There they cancel. And then here they're going to join, right? That section where they phase through each other, where the two waves work through each other, right here. See how they're starting to build up on top of each other? That's known as constructive interference. And so that's what this diagram here shows, right? Constructive interference makes things louder. We've already learned this concept. It's called resonance. Only resonance occurs where you have a wave that's overlapping. Right here, I just have like a pulse that's overlapping, right? The destructive word, by the way, would be if I were to kind of let this play again. There's going to be see how this is going to work? There's going to be a deconstructive interference right here because as they phase through each other, oh, I didn't even catch it. Let's try it one more time. And right there. See how that worked though? At one point there, I wasn't fast enough, but you should have literally seen it be like a straight line straight across. That's destructive interference, right? So, the principle you need to know is something called superposition, which sounds really cool, superposition. But it states that the displacement of each combined pulse will be the sum of the displacements of the individual pulses. Basically, you're adding things together. If you have a blue and a purple pulse here, they're going to add and become this red pulse, right? Because really what's happening is this height right here and this height right here kind of add to stay there, right? This height and this height add for there. This height adds for there. This height and this height adds for there. But the same thing happens in the negative direction. Here you have this one and this one, so it ends up there. Here these things are equally far apart, so it's a node almost, right? Remember the word node from a previous day? Where this is kind of right in the middle. That's destructive interference. So most kids pick up on that pretty quick. What I'd like to do right now is kind of just play with the simulator for a bit, because it's kind of a cool little thing to work with. I want to just show you a few things. Let's restart at the beginning here, right? So this was a loose end, and if I shoot a pulse up and down like this, if there's no resistance, it should basically reflect on itself and come back. And that was with the loose end, right? So this allows it to go up and then back, right? If I put a fixed end on, it's then going to go around in a circle, basically. See how it kind of goes around like that? So that's when I put it on pulse. That was one pulse like this. But what if I oscillate it? Well, watch the oscillation. If it goes up and down like this, well, now something really cool happens. See how it's getting bigger and bigger and bigger, and they're kind of all in sync? And then it gets a little messy for a little while. That doesn't work as well. But let's restart this again, right? And I'm just going to pause. Okay. See all of these little green dots right here? These are nodes. They're the ones that are right in the middle. In theory, these ones aren't even moving as these waves kind of work through each other, right? And there's constructive and destructive interference. The destructive interference is right at these green dots. That's where everything's been destroyed. But the constructive interference is right here where they're getting bigger and bigger. And watch, right now they're about, well, you can see how far, that's how big they are, right? What if I play this a little bit longer? See how this wave's starting to get bigger? And now they're this tall here, right? Now these aren't perfectly in phase. Unfortunately, I haven't set this up quite right yet so that they're perfectly in phase. But what we are seeing is resonance, where we're seeing waves added on top of waves, right? And right here, as I just pause, right, there's a good one, right? See how this is nice and tall right there? That's a nice amount of positive interference. Let's restart this again, right? Look at this. So as they get taller and taller, these waves are building. This is basically the principle that caused that one bridge to collapse. Now look at the green dots, right? These things are perfectly in sync when those green dots aren't moving. So right now they're perfectly in sync. And you notice that they keep getting taller and taller, right? Like when I first started art, they were kind of small, but now they're getting higher and higher. The amplitude is increasing. One more time. Right? Minimal amplitude, and then look at these green dots. See how the green dots right there? Right there. How they're all in line? This is now in phase. Now, it's not a perfect match, but it's getting taller. Right? And now they're back in phase again. See how all the nodes are back on their spots there? It's back in phase again. There's constructive. And look at the height of this wave. It just keeps getting taller and taller and taller. Isn't that cool? Right. Now let's try this again with not just a manual one, but let's try the loose end, right? See what happens here now. So restart and then oscillate on a loose end, right? So same sort of thing happens here, right? These are, sometimes they're going to all be in phase. Now look, they kind of cancel each other out there, right? Oh, now we're getting back to be in phase. See, they're getting taller again. And I bet you in a little bit here, they're going to cancel each other out again. No, not canceling. It'll reach that point at some point, right? Where it gets taller and taller and taller. Kind of an interesting one is where there's no end. And then this just basically just sends a wave straight out, right? And this is basically the kind of wave that like electromagnetic waves send out when we have light or radio or microwave or X-rays. This is what they do. They send a wave out just in a continuous thing. And that's actually the topic of our research project, the idea of trying to figure out what electromagnetic wireless signals are useful for, right? But if we put an end on it, well, then they can start reflecting back again. And that's got some cool properties, right? That's where they can interfere with each other. So hopefully I've shown you that well enough. If you are able to and you'd like to, I've got a YouTube link right here to a video. It's not really going to be very practical for me to show you the whole YouTube video, but I'm going to click on the link, and then you can click on this yourself. This is kind of a cool little one right here. I just have to let this open up here. It's basically a science teacher who decided to set up a whole bunch of pendulums, all of different lengths. And what's kind of cool is as these bowling balls go back and forth, all the pendulums are different lengths, you can actually see the wave go back and forth and back and forth. It's not really interfering necessarily because of the fact that like they're all individual pendulums, but it's kind of cool to see how they're all like they're taking off and working. And if you keep watching this video, they'll eventually start to line up and you'll see some cool patterns of this. So one of the downsides to making a video with a video in it is that I really hope that YouTube doesn't make me take this down because of the fact that I'm embedding somebody else's video within my video. But I'll let it play for just a few more seconds. It's actually a 3-minute video, but you can kind of see they're almost starting to line up again, with like kind of a pattern back and forth. At one point, they separated into two lines. So if you've got an extra minute and a half, try this YouTube link. Oh, look at that, look at that. See all these lines right there going back and forth? That's kind of cool how the pattern works. And then they just start to weave again. And eventually it gets to the point, I'll skip to the end of the video here, where they actually start to remake a wave again, which is kind of cool. So anyways, that's not really the main point. But if you'd like to, you can watch that video on waves. So to make sure I've really emphasized this point, because guys, I'm nearly done. This is our concept. If you have two waves that are moving towards each other with positive pulses, they'll add to each other, right? They will phase through each other, and whatever height you had of A, you'll still have that right here. Whatever height you had of B, you'll have that over here. And so constructive amplitude makes things bigger and bigger and bigger, louder. But you can also dampen certain sounds. And if you dampen certain sounds, you have negative interference. So what we watched then with a reflective wave, what we saw in the one little applet I played with, we were creating what's called a standing wave. But the only way this works is if the timing is just right. Okay, you have to have it fit just perfectly, and the app I was using wasn't quite perfect. It was close, but it wasn't quite perfect. Let's show it one more time here. I'll just restart this thing here. As it goes up and down like this, you'll see, oh yeah, that looks good. That's a standing wave. It's getting bigger and bigger, but it's not quite perfect. A true standing wave would be like you wouldn't see it grow quite as in the same pattern. One more time from the top here. Let's actually throw it on the loose end and restart. All right, as it goes up and down, you can see how it got bigger there all of a sudden, right? And now it got smaller. It's not quite perfect the way it works. And if I go back to the fixed end here, well, now it's gonna be all over the place. Oh, see how there's constructive interference now? Look at those green nodes. When the green nodes are actually standing in the same spot, it's a perfect standing wave. And so I don't have a standing wave right now. Oh, I just missed it. There was one there. Let's restart one more time. I'm gonna find you a standing wave right there. See how it's perfectly flat? Oh, that's perfect. That's a standing wave. A standing wave should be perfectly flat for a second, and then it should be bigger. This is not quite perfect. You can see how this node is right out of place here. But for the most part, the rest of this, it's bouncing up and down perfectly in sync. It's called a standing wave. Now it creates nodes and antinodes, just like we've described, right? So the nodes are right in the middle here, those little green dots. And the antinodes are basically how the tops and bottoms of this wave as it goes up and down and up and down. And like I've been saying, this is resonance. The frequency matches each other. Now, where's the application? Musical instruments. Yeah, that's really the main one. Musical instruments often rely on air resonating inside of some sort of column, some sort of tube, whether it's a flute, whether it is a French horn, a trombone, a tuba, it really doesn't matter, but if you're blowing into some sort of instrument, there's a standing wave vibrating inside of that instrument. Now, what you guys need to know is that the standing wave that's bouncing back and forth inside of this only is a fourth as big as a normal wavelength. And the reason why is that you need a wave to basically go all the way here as an open, hit a node in the middle here, and bounce back again. And that's not a full wave, because a full wave would be all the way up, all the way down, and all the way back again. And we don't need it to go all the way up, all the way down, all the way back again. We actually just need it to go that far. Because if you have a quarter of the wave, if it goes from here to here, then it can bounce back. And that's all we require. If you can kind of see that visual right here, that's as far as this requires. And then it's going to hit, and it's going to bounce again. Maybe the better way of showing it is not in this sort of orientation, but to show it more like this. It's going to go like this, and then rather than needing to go up and back down, it can just bounce back out the other way like this. And so this is your instrument right here, like this. And so yeah, you need a quarter of a wavelength. That's what you need to have. The closed end is a node, and there's antinodes on the open end, and that tells you what pitch. For those of you who know music, that tells you what pitch this is going to have. Okay, you know the formula we've been working with: velocity equals frequency times wavelength. It's called the universal wave equation. The velocity at which sound is resonating, we'll talk about that in a second here, is based on the frequency and the wavelength. Well, however long your tube is, whether it's a trombone, a trumpet, right? And often like a trombone is the classic example, because as you move the slide forward and back, it lengthens or shortens the tube. That changes your wavelength that fits inside. And if you change your wavelength, it changes your frequency. So it's 1/4 of a wavelength if it's an open, or so if it's a closed open column. A closed column is, that's actually what I just talked about here. Yeah, a closed column is, it's always 4 times. It's a quarter as much. I'm getting ahead of myself because we're going to do open columns in a second. But here's a wavelength. And this right here is a quarter of a wavelength. A quarter of a wavelength fits inside and comes back. Now, in theory, you can actually do 3/4 of a wavelength. You can have it go all the way up, that's half a wavelength, come halfway down, and then bounce down the other way. And that's 3/4. Anything that's in a quarter increment are the overtones and harmonics that you can have when you have a closed tube. But if you have an open tube, the geometry, the way the waves fit is a little differently. If both ends are open, you always need to end on antinodes. Okay? If it's ever closed, the closed end has to end on a node. But if you ever have open ends, they both have to be antinodes, which means you need to have either half a wavelength or right here. This is actually a full wavelength. It went all the way up and all the way down, so you need increments of half wavelengths. And that's how you can tell what frequency you're going to play. So I've got one last example, then we're done. This is actually a really short lesson. If you understand the concept behind a standing wave, though, that's what we're looking for. So imagine that you have an organ column. If you know like an organ, right? A big piano-like structure, and it's got all of these pipes, right? So all of these pipes here that are together, they all produce a different sound, right? And then a person sits down at a piano-looking thing here. Draw a bit of a piano. 3 black keys, 2 black keys, something like that, right? There's an organ. It's not a bad organ, actually. Good job, Chris. And what I need you to know is that if you have an open-ended column, open-ended means that both sides of the pipe are open, so that means that we need it to look like this. We need it to bounce back and forth so that they both end on the open side. It's got to be open and open, okay? It can't go like this. It can't go in and hit like that because there's nothing for it to bounce off of. And so it could just go like this and like that. That could be how your wave kind of works. I threw an extra one in the longer tube there. But unless there's a close on the top, this one that I drew here won't work. Long story short, you just need to know your math. And the way it works is that it's 1/2 of a wavelength. That's how it works. It's 1/2 of a wavelength that fits inside there is equal to your length. The length of your tube is half of a wavelength. So if we know that the length of our tube is 3.6 meters, and that's equal to half a wavelength, if you were to times both sides of your equation by 2, it means that a full wavelength would be 7.2 meters. That's all you need to do, is you times this number by 2, or you times that number by 4. You times it by 2 for an open tube, or 4 for a closed tube. That's it. Okay. If you've ever seen those boom whackers, those are like those tubes that you can kind of hit on the ground. The longer the tube, the different the frequency. And so actually if you use like a tube that's half as long as another one, you actually get octaves apart, which is kind of cool for those of you who know what an octave is in music. So yeah, lots of musical instruments are based on this principle. Anyways, long story short, now that I know that my wavelength, I just need to use the universal wave equation. Velocity is equal to frequency times wavelength. If I want to know what frequency this organ is going to play, it's velocity divided by wavelength. And the speed of sound is roughly 330 meters per second. And the wavelength that I need to use, we just said was 7.2. Right? The half wavelength fit into the 3.6 meter tube. So I just need to divide 330 by 7.2, the full wavelength, and I now have a frequency of 45.8 hertz. And you can kind of see that just as you change the length of your tube, it's going to change the frequency you have. And so this is a very long tube. That's probably a very low note in terms of its pitch. Maybe even so low, maybe even we can't hear it. I don't know what the lower threshold of frequency is for us hearing, right? But let's say that this tube was a little bit smaller, not 3.6, but let's say this was a flute, right? And a flute is a much smaller distance, right? Like, let's say that your flute is, I don't know, like 2 feet. It's less than that probably even, right? Any instrument that's smaller than that. We could change this out and not make it a 3.6 meter instrument. We could make it like a half a meter long. You still have to times it by 2. So if you took that and times it by 2, then I guess if you had half a meter of an instrument times by 2 would be 1. So you could take 330 and divide by 1. Well, then it would be 330 hertz. And that's a bit of a higher note, right? And basically that's what's happening is as you lengthen or shorten the tube, the instrument that you're playing in, it changes the frequency or the pitch. And so that's kind of cool. There's like a musical overlap. So, okay, I literally just hit the 20-minute mark right here, and that's exactly what I'm going for right now. So if you have any questions, as always, make sure you ask. This was not meant to be a lesson that's supposed to take overly long, and that's why I like to make this one a YouTube video. That way you have the ability to kind of work on this one at your own pace. You can watch this one at home, and hopefully we'll have some time today for you to in class work on different tasks like different labs or assignments that are needed. So if you have questions, ask me questions. If you have questions, ask me questions, of course. Otherwise, thanks for watching, everybody, and we'll talk soon.